We're going to take a look at some physical applications of calculus now. We know from physics that mass is equal to density times volume, work is force times distance, and force is mass times acceleration. But when we use those formulas, we're generally working under the assumption that the quantities involved in them are constant. So let's examine what happens when those quantities vary. In our first example, we'll look at the mass of a thin object whose density varies according to some function d equals rho of x. So imagine we have a thin wire. We know that its density is variable across the length of that wire. We want to know the mass of the object between 2 points on the object A and B. We're going to use techniques similar to what we've done before. We're going to divide our region up into smaller intervals. On each of those intervals, we can use our formula for mass equals density times volume in order to calculate or estimate the mass of the smaller segment. So here we divide our region up into n intervals. Each of them has width delta x, which is b minus a divided by n. And then we can take the mass of each that's going to be approximately equal to delta x, which is the width of the region, times rho of x sub I, which is the density of the wire or the object on the ith interval we've created. Here we're making the assumption that because our wire is very thin, that the volume is approximately the same as the width. So we can use summing techniques like we've done before to say that the mass of the region from A to B is going to be approximately equal to the sum of the mass of each of these smaller segments. So that's the sum from I equals 1 to n of rho of x sub I times delta x. If we let the number of intervals go to infinity, we can then compute mass using an interval. It'll be the interval from A to B of our density function rho sub x dx. If we want to compute the entire mass of an object of length L, we would just compute the integral from 0 to L of rho sub x dx. Let's look now at a specific example of our formula for calculating mass. Here we have a 3 meter long thin bar whose density varies according to the function rho of x equals 2 plus x kilograms per meter. The mass then is the integral from 0 to L, where L is the length, of rho of x, the density function dx. That's the integral from 0 to 3 of 2 plus x dx. Finding antiderivatives, we get 2x plus 1/2 x squared from 0 to 3, which gives us 6 plus 9/2, which is about 10.5 kilograms. We can apply similar reasoning to examine the work done when a force varies. Let's look at a way to find the work required to move an object on a straight line from position A to position B if the force used to move whatever the object is varies according to the function y equals f of x. Here, we'll divide our distance on our interval into n smaller subintervals. Each of those is going to have length b minus a over n, which we'll call delta x. We can then approximate the work done on each of these smaller intervals using our formula work equals force times distance. So on each interval, the work done is going to be F of x sub I times delta x. We can then approximate the work done over the whole distance by adding these up. Our total work is going to be approximately the sum from I equals 1 to n of F of x sub I delta x. Letting n go to infinity, we get that work is the limit as n goes to infinity of this sum, I equals 1 to n of x sub I delta x, which then gives us that work is the integral from a to b of f of x dx, where f of x is our force function. Let's look at an example of this. A force of 8 newtons holds a spring at x equals 0.08 meters from its equilibrium position. We're going to use Hooke's law to find the work that's required to stretch the spring a half a meter from its equilibrium position, and the work required to compress the spring a quarter of a meter from its equilibrium position. Hooke's law tells us that the force required to keep a spring in a compressed or stretched position, x units from its equilibrium position, is f of x equals k times x, where the positive spring constant k measures the stiffness of the spring. First, we'll find k in our particular example. Hooke's law tells us that f of x, the force required to hold the spring, is equal to some constant k times x. We know that when x is 0.08, that force is 8 newtons, so we get that f of 0.08 is equal to 8, which tells us that 0.08 k equals 8, and solving that for k, we get that k is equal to 100. This then tells us that our force function f of x is equal to 100x. To stretch the spring from its equilibrium position to a half meter out, the work required is going to be the integral from 0, which is equilibrium, to 0.5 of f of x dx. That's the integral from 0 to 0.5 of 100x dx. Taking an antiderivative, we get 50x squared evaluated from 0 to 0.5. Plugging in, that's 50 times 0.5 squared, which is 50 times a fourth, which gives us 12.5. Our units for work are joules. To compress the spring, our work is going to still involve a very similar integral. We're going to also integrate from 0, the equilibrium position, to our upper limit is going to be negative 0.25. This is because we're compressing the spring. We use our same force function here, f of x dx. So we have the integral from 0 to negative 0.25 of 100x dx. The same antiderivative works. We get 50x squared from 0 to negative 0.25. Plugging in, that's 50 times negative 0.25 squared, which is 50 divided by 16. And so we get 3.125 joules as our answer there. Our next application involves investigating the amount of work required to lift a rope or a chain L units upward. As we lift the rope, the mass of the rope or chain is going to change because there's less hanging down. Similarly, each segment of the rope has to travel a different distance. We know that work is force times distance. We'll break force down into mass times acceleration. Here, the acceleration acting on our rope or chain is acceleration due to gravity. The mass of our rope or chain is going to be its density times its volume. Density will be given by some value or function rho. Volume, for the purposes of these questions, we'll assume is approximately equivalent to the length of the segment. So if we imagine our rope or chain, we're going to lift it a total distance L. As we've done previously, we're going to break up our rope or chain into a series of segments that are each smaller, and we're going to contemplate what is the work required to move each particular segment. So if we take the segment K here, and we investigate what its mass is, that mass is going to be approximately the density of the rope at that point times delta y. Delta y here is the height of each of the segments that we've created. This then tells us that our force is rho of y sub k times delta y times acceleration due to gravity. Our work then is going to be that force, rho of y sub k times delta y times g, times the distance we have to move that particular segment, which is going to be given by the total distance minus the height of that segment. Using techniques similar to what we've been using, we now know that the work to lift each individual segment is approximately equal to rho of y sub k, the density of the segment, times g, acceleration due to gravity, times delta y, the height of the segment, times L minus y sub k, the distance we have to lift the segment. Therefore, the work to lift the whole rope or chain is going to be equal to the sum of all of these individual segments. So that work is approximately equal to the sum from k equals 1 to n of rho of y sub k times g times L minus y sub k times delta y. We use our calculus trick of taking a limit. We're going to let work equal then the limit as n goes to infinity of this particular sum, k equals 1 to n of rho of y sub k times g times L minus y sub k times delta y, which we know is equal to the integral from 0 to L, if we're lifting from the ground all the way up to a height of L, of our density function times g times L minus y dy. Let's look at an example here. We have a 60-meter long rope. It hangs freely from a ledge. The density of the rope is constant, 55 grams per meter. How much work is needed to pull the entire rope to the ledge? Our units for force and for work involve newtons, and a newton is 1 kilogram times meters per second squared. 1 kilogram meter per second squared. So we need to convert our density function into kilograms rather than grams. 55 grams per meter multiplied by 1 kilogram over 1,000 grams tells us that our density function is 55 over 1,000 kilograms per meter. So the work required to lift this rope is going to be the integral from 0 to 60, since we're lifting 60 meters, of our density function rho, 55 over 1,000, times gravity, which is, we'll see in a second, is 9.8 meters per second squared, times 60 minus y dy. We can pull the 55 over 1,000 and the constant acceleration due to gravity as 9.8 out in front. So we have 55 over 100 times 9.8 times the integral from 0 to 60 of 60 minus y dy. We now have 539 over 1,000 times the integral from 0 to 60 of 60 minus y dy. Our antiderivative is 60y minus 1/2 y squared, evaluated from 0 to 60. We have 539 over 1,000 times 3,600 minus 1,800. This gives us approximately 970.2 joules. Our next application explores the work required to pump water from a tank to a level H above the tank. So here we have our imagined tank. It's generally some shape for which we can determine a cross-section. We're going to pump the water to a height above the tank, illustrated by our purple segment here. We're going to call that height H. We know that work is equal to force times distance. Here our distance is going to be h if we're considering the total distance. Force is always mass times acceleration. Our acceleration is once again going to be acceleration due to gravity, the force that is holding the water down into the tank. Our mass is the density times the volume. Here, density is once again going to be given by a function rho. Typically, if it's water, we're going to be looking at the density of water. The volume is going to be the area of a cross-section times the height of that cross-section. So once again, we're going to divide our container up into smaller segments. Each of these segments is going to represent some cross-section of water. We make n slices out of the tank, and what we're going to investigate is the work required to pump one particular slice out of the tank. So for our representative slice, to calculate that work, we need to understand the density, volume, and distance for that slice. So breaking down work again into force times distance, we can then break force down into mass times g for acceleration due to gravity times distance. The mass is going to be the density times the area times the height, that gives us the volume, times g times distance. Our density is given by rho of y sub I. Our area is going to be the area of that cross-section. The height of our cross-section is going to be given by delta y. G is acceleration due to gravity, and the distance the slice has to travel is going to be the total distance minus the height at which that slice sits. Putting that all together, we can see the work for that slice is rho of y sub I times the area of y sub I times acceleration due to gravity times h minus y sub I times delta y, which is the height of our slice. So given what we know about the work for each slice, we can then use that to figure out the work for the entire container. We're going to add up the work for each slice to get an approximation of that work. So our total work is approximately the sum from I equals 1 to n of rho of y sub I, the density function, times a of y sub I, the area of a cross-section, times g, acceleration due to gravity, times h minus yi, the height that particular slice has to be pumped, times delta y, the height of the slice itself. Letting n go to infinity, we get that work is that limit as n goes to infinity of the sum of rho y sub I, a y sub I, times g times h minus y sub I delta y, which again turns work into an integral. Work is going to be equal to the integral from a to b of rho times g times some area function times h minus y dy, where a and b represent the starting and ending point of the quantity we're trying to lift. So imagine we have a water trough that has a semicircular cross-section with a radius of 0.5 meter and a length of 4 meters. How much work is required to pump the water out of the trough to the level of the top of the trough when it is full? What we're going to do is envision the end of this trough on a coordinate axis. So I've placed it so that the top of the trough is lying along the x-axis, the bottom of the trough is 0.5 meter down, and I've drawn in a representative slice here. Because it's semicircular, we know that the equation of that circle is x squared plus y squared equals negative 0.5 squared. So x squared plus y squared is equal to 1/4. We can use this to help us find a width of a given slice. Once we know the width of that, we can compute the area of a cross-section. So the width of a slice is 2x if we consider the x coordinates of the endpoints. But here, if we use our equation, we see that x is going to be equal to 1/4, or the square root of 1/4 minus y squared. So the area of any given cross-section is going to be 2 times the square root of 1/4 minus y squared, which is the width of the cross-section, times 4, which is the length of our trough. We can tidy that up to be 8 times the square root of 1/4 minus y squared. So we have our area function for our cross-section. Now we need to contemplate the remaining pieces of our work integral. Rho of y here is just going to be the density of water, which is 1,000 kilograms per meter cubed. G is once again acceleration due to gravity. Since we're measuring everything in meters here, we'll use 9.8 meters per second squared for G. The distance that any particular slice needs to be lifted is going to be given by its y-coordinate. Since it's sitting below the axis, the remaining distance to lift it will be given by its y-coordinate. So our height is going to be equal to y. So now we can construct our work integral. We can see that the work required is going to be the integral from 0 to negative 0.5. We're lifting, or negative 1/2. We're lifting from a height of 0. So we use a negative 1/2 at the top of our integral. We have 1,000 for rho, 9.8 for g. Then we have our area function and our height function dy. This becomes the integral from 0 to negative 1/2 of 9,800 times 8 times the square root of 1/4 minus y squared for area times y for the height. Now we'll go ahead and calculate our integral. So we saw that work was the integral from 0 to negative 1/2 of 9,800 times 8 times the square root of 1/4 minus y squared times y dy. We can pull the 9,800 times 8 out in front. That gives us 78,400 times the integral from 0 to negative 1/2 of the square root of 1/4 minus y squared times y dy. We're going to solve this with substitution. So we'll let u be the inside function, 1/4 minus y squared. That means that negative 1/2 du is equal to dy. So our integral now becomes 78,400. I'm going to switch my limits from y to u. So when y is 0, u is 1/4. When y is negative 1/2, u is 0. So now we have 78,400 times the integral from 1/4 to 0 of u to the 1/2 times negative 1/2 du. Moving the negative 1/2 outside, we get negative 39,200 times the integral from 1/4 to 0 of u to the 1/2 du. We'll take an antiderivative now, and we'll get 2/3 of u to the 3/2, and we're going to evaluate that from 1/4 to 0. Plugging in 0 gives us 0, so we have negative 39,200 times 0 minus 2/3 times 1/4 to the 3/2. 1/4 to the 3/2 is 1/8. So we get negative 39,200 times negative 2/3 times 1/8. Working that out, we see that we get 3,266 2/3 joules. Our next application involves examining the force exerted by a body of water on a surface. In particular, we're going to imagine a dam, and we're going to try to figure out the force that water applies to that dam. As in our other applications, we're going to consider the force on some part of our dam. So here we have a very poorly drawn dam. We're going to divide the dam up into strips, and we're going to consider the force on a single strip, construct a formula for that, and then use that. We'll think about force a little bit differently here. We're going to consider force as pressure times area. So we'll examine the pressure on a given strip as well as the area of its strip. Pressure can be expressed as rho times g times h, where just as we've used for all of our other examples, rho is going to represent the density. Since we're talking specifically about dams and water in this case, rho is typically going to represent the density of water. If our dam is being pushed by some other substance, we can use that density instead. G is going to be our usual force due to gravity, and H is going to be the depth of the strip that we're considering along our dam. Interestingly enough, even though we're using acceleration due to gravity, the pressure doesn't matter whether the surface we're pressing against is horizontal or vertical. All right, so if our dam has a height of h units, then the depth of our particular strip is going to be represented by h minus y sub I. So we can see now that force is going to be rho times g times h minus y sub I times the area of y sub I, which is going to depend on the shape of our dam. In particular, our area is going to represent the width of the dam at our particular height y sub I times delta y, which is, of course, the height of the strip as we've divided up our dam into equal sized strips. So force is rho times g times h minus y sub I times the width of our strip y sub I times delta y. So given force equals rho times g times h minus y sub I times w of y sub I times delta y, we can say that the total force is approximately the sum of all of the forces on the individual strips we created. So we get that force is approximately the sum from I equals 1 to n of rho times g times h minus y sub I times w of y sub I times delta y. Then the force is exactly equal to the limit as n goes to infinity of this sum. Remembering, of course, that h is the total height of the dam, and w of y sub I represents the width of each segment. So we get that the total force on our dam is the integral from 0 to a, where a is the height of the dam, times rho times g times h minus y times w of y dy. Let's look at an example. Here we have a dam whose lower edge is a parabola defined by the function y equals x squared over 4. The dam is 25 meters tall. We want to determine the total force of the water on the dam. Lengths are measured in meters, and the water levels at the top of the dam. So given our formula, we can see that the top corner of the dam must be at the point 1025, because we're told that that dam is 25 feet tall. We're going to look at a representative slice here and see if we can construct a formula for the area of that slice. Given that y equals x squared over 4, we can see that for y equals x squared. So the x coordinates of all of the points on our parabola are given by plus or minus 2 root y. That means that the slice of our width, or the width of our slice, must be 2 times 2 square roots of y, or 4 square roots of y. The depth of the water at our given slice is going to be 25, the total height of the dam, minus our y coordinate. So we get that force is equal to the integral from 0 to 25 of rho times g times the width times the depth times dy. That's the integral from 0 to 25 of 1,000, the density of water, times 9.8, the acceleration due to gravity, times our width function, 4 root y, times our depth function, 25 minus y, dy. That gives us 9,800 times the integral from 0 to 25 of 4 root y times 25 minus y, which we can simplify to be 100y to the 1/2 minus 4y to the 3/2 dy. We'll take some antiderivatives now. So we have 9800 times the quantity 200 over 3 times y to the 3/2 minus 8/5 of y to the 5/2 evaluated from 0 to 25. We're going to slow down a little bit here as I evaluate these large numbers. We have 9800 times the quantity 200 over 3 times 25 to the 3/2 minus 8/5 25 to the 5/2. Plugging in 0 cancels out both terms. So we have 9800 times 25,000 over 3. 25 to the 3/2 is 5 to the 3rd power. And then 8/5 times 25 to the 5/2 is going to be 25,000 over 5. Doing some work with a common denominator and such gives us our final result. We see that force applied on this dam is going to be equal to 9800 times 1000 over 3 which is a really large number, 9,800,000 over 3, or approximately 32,666,666.67 joules.